Hello and welcome to another video. In this video we're going to be looking over the third problem of the Biweekly Contest 123, maximum good subarray sum. And I think this is actually a pretty good problem. I think the last few problems that were the third problem of the contest were kind of like too easy. I think this one's pretty good. So in this one you're given an array nums of length n and a positive integer k, and a subarray of nums is called good if the absolute difference between its first and last element is exactly k. In either words, nums I to j, nums I minus nums j equals k. Return the maximum sum of a good subarray nums. If there's no good subarrays, it returns 0. So here's the first example, and they show you like what are all the valid subarrays. So you can see that the difference between the first and last element in the subarray is 1, and the biggest subarray is 5, 6. So you want to return the sum, which is 11. And in the second example, there are a bunch of subarrays as well. So there's negative 1, 32, 2, 4, 5. The biggest subarray sum is 2, 4, 5, and that gives you 11 as well. And in the third one, you want a difference 2. So here's some good subarrays. So you can see it's like negative 1, negative 2, 3, or negative 2, negative 3, 4, and the maximum subarray sum is negative 6. So you do want to include any sum you find. So if the sum is negative, you still want to include like the best one. You only want to return 0 if you didn't find anything at all. And yeah, so there's kind of like a few parts of this problem, and we're going to go through an example here. But essentially, for a number, this is kind of like a more like two sum with a bunch of more steps. So for a number, we need to look at basically look at like what's the complement of that number. So for example, let's walk through kind of like one of these numbers. Let's say we're on number 8. And the way we're going to do this, kind of like two sum, is we will just go through all of our numbers, and going through that number will represent the subarray ending with that number, and then we'll get all the subarrays there, right? So because they're contiguous, to get all of the subarrays, you can just, usually the way you do it is you say, okay, I'll just go through every index, and that index will be the end of my subarray or the start of the subarray. And if you go through every index and you get every subarray that ends of that index, then you will get every subarray. So for k equals 2, for example, let's say we're on this element. This element is 8. So what values, instead of like manually going through here, we will just look kind of like two sum, like I said, we will just look for like, does the complement exist? So what we need is, this is 8. So this is the j value. So we need an I value such that I minus 8 equals 2. And you can basically have a, I'm not super, like, I haven't done absolute values in a while, but I think what this ends up being is, this ends up being like this, equals plus or minus negative 2 whenever you have an absolute value. So let's just double check that really quick. So if it's plus 2, that means I can be 10, and 10 would work. And if it's negative 2, then it would be 6. So let's see what happens when we put in 6 here. So we would get 6 minus 8, and this would give you negative 2, and this would be 2. So yeah, that is correct. So basically the idea is you want to get an I such that the value is negative k, and you want to get an I such that the value is k. Now I think k only has to be positive, so because like obviously an absolute value can never be negative. But essentially it's like two sum, but instead of having one complement, you have 2. So basically we look for a number, so that part it should be kind of clear, for a given index. For a given value, actually, we're going to look for both k and minus k complement values. So for example, for this, we're going to look for, do we have a 6 somewhere here, and do we have a 10? And we don't have either, but that was just an example. So let's say only one of these values exists. Like let's say, for example, we're at this 3, and let's just pretend none of these exist, but we just say like, oh, look, we do have a value 1 at some index that, because 1 minus 3 will be negative 2, right? So we look for, once again, we look for two values. We can look for 1 and we can look for 5, because 5 minus 3 will be 2, and 1 minus 3 will be negative 2. And absolute value of both of those is 2. So we look like, do we have a 1 in here? Let's say we do have this 1 over here. How do we get a sum? Like we have to get a sum here in O of 1 because our array is 10 to the 5th. So we have to like, as we go through here, we basically need like a linear time solution. So how do we get a sum in linear time? That part should be pretty straightforward. You just do prefix sums. So you can just prefix sum this entire array, look for where the 1 is, And if you know the ones over here, you can get this sum in O of 1 with prefix sums, because none of these values will ever be changing. So you can just like compute the prefix sums ahead of time or on the fly. Either one's fine. So now that that part is solved, we kind of like, let's write down what we have. So for a given number, calculate I such that I minus, or so for a given number j, calculate I such that I minus j equals k, and I minus j equals negative k. And these will be the two numbers we look for, right? These will be the two numbers we look for. And if they both exist, like let's say here we're looking for a 3 and a 5, like if they both exist, we can be like, okay, where's the 3? Where's the 5? Or not the 3. Where's the 1? Where's the 5? Let's get both of those subarrays, whichever one's bigger is going to be like our answer. But the problem is, like, look at the situation that we have now. So we have a 1 over here, we have a 1 over here, and we have a 1 over here. So what happens if you have multiple locations where you have a 1? And that's kind of the tricky part, right? Because imagine your array is repeating. Like, what if it's just 1s and 3s? Then for a 3, you'll have like 10 to the 5th over 2 1s, and you can't just like check them all, because then you basically have an n squared solution. So how would you do that? In this part, you basically want to say, okay, well, I want the one with the biggest sum. So let's just think about, like, for each one of these, like, what is the sum going to include? So let's say we have this one. The sum is always going to include every number from our old element up until our current point, right? So like from this element, it'll be here, from this element, it'll be here, from this element, it'll be here. So basically what we can do is whenever we reach a new one, or whenever we reach a new value that we already have, like let's say we have this value already at some index that we have stored. We're just going to store like the value in an index, kind of like toSum, like I said. But let's say we reach this value and we're like, well, which one of these do we want to keep? The way this is going to work is because our sum is going to be, like I said, the sum from the value that we pick all the way up until, you know, the value that we're picking. It's basically going to be like the whole thing. So if we pick this one, then the sum will start here, and then it'll go all the way up to, like, let's kind of draw another color. So if we pick this one, it'll be up to here. Let's say it's up to the 3. It'll be like this. But if we pick the old one, then it'll be the old sum. So you see the difference is basically this part here, right? The difference is basically the sum up until that number. And so we can easily just calculate this sum. So whenever we have a number stored and we reach it again, we can just calculate, okay, what's the sum between those? So like this sum here. And that's going to be the difference. And if this sum is negative, then we're going to want to start here. But if this sum is positive, then this will add on. So this is kind of like a Cadane's algorithm, right? Where essentially we're saying, okay, let's take our old number. Let's see if that old number, the sum that old number is contributing that the new number won't be contributing is positive. If it's positive, we're going to want to keep the old number. But if it's negative, then we're going to want to get rid of that old number. So like in this case, this sum that this is contributing is negative 10. So in that case, we would say, okay, well, we don't want that number. We want this number. Then when we get to this number, we're going to say, okay, where was our old number? Our old number is over here. What's that sum that contributing to this number won't be? It's going to be this chunk here. And you can just get the Snow one with the prefix sums. Now this is positive. So between these two, we're going to want to keep this old one because this is contributing a positive sum. And then once we get here, we're going to say, where's the location of the one? It's going to be this one over here. This is going to be the best one. So let's do like a dry run of the algorithm now. I think that's most of it. So that's the main thing you need to do is you need to do prefix sums to get sums in O of 1. And whenever you hit a number multiple times, you do the Cadane's thing of just figuring out what sum that old number contributes. If it's positive, keep the old one. If it's negative, throw in the new, use the new one. That way you will only at one time for each number have one location. And then for each number that we're checking, right? So if we check for 3, we can check for, like I said, remember we want I minus 3 equals 2 and I minus 3 equals negative 2. So this is going to be 5 and this is going to be 1, right? So we check, is there a 5? No, there isn't. Is there a 1? Yes, there is. But either way, even if there's both for every number, you're at most checking two locations, getting that sum in O of 1. So this is going to be an O of n function now with those two optimizations. So let's walk through this and how it'll work. So here, And I'm going to have a prefix sums. Yeah, so I'm going to compute the prefix sums on the fly. So yeah, so I'm going to actually, let me think, I could do that. I can just do it over here. So we'll just compute the prefix sums right below this. Let's actually move this down. And let's move this down here. There we go. And we can get rid of like all of, actually be even faster to just get rid of all of this and just put it in a new array. New array, same thing. All right, close enough. So this will be our prefix sums that we'll be computing on the fly, and the prefix sums, I'm going to use an object, so the prefix sums at location -1 will be 0, just like, because we want to get like the sum of the whole array at some point. So like, let's say we're here, if we want this whole sum, then it's going to be sum of 5 minus -1, which we have stored here. Okay, anyway. So we run into 1 and we check, okay, is this 1, like, did we have it before? No, we don't. So we're going to have two things. We're going to have the prefix sums and we're going to have a dictionary of locations, kind of like a two-sum cache, basically, just like a number and its index. So we don't have a 1, so we'll put 1 is at index 0. Do we have the complement of 1? Well, obviously not, because 1 is at index 0, so we don't have to check for that. We can just skip that. Okay, let's get rid of this. Let's get rid of this. Let's just actually use a thing here. There we go. Okay, and let's move this over here. So this will be our cache that we're just storing our numbers. Okay, whoops. And then what we want to do is we want to check here. So do we have a -5? No, we don't. So -5, index 1. Oops. And we are going to be computing the prefix sums as we go. So this will be 1, this will be -4. Okay. Do we have any value? So we basically need to have like -3 here, I think, or -7. Yeah. Yeah, I think so. And we don't have anything here, so yeah, we don't need to do that. Okay. Here we compute our prefix sums. So this will be -10. Do we have, what do we need here? We need -4, I think. Right, so we basically need, yeah, we need -4 and we need like -8 or something. We don't have either of those, so we're going to store this at location 2 and move on. Okay. Do we have a 1? Yes, we do. So we have a 1 at index 0. So let's get the sum up until before this one. Let's actually move it like this. There we go. So let's get the sum up until like from where the 1 is at location 0 to this location here, just this prefix sum here. And so this prefix sum here is -10. So that's negative. So we're not going to want that number. We're going to want this number. So we will replace the location of 1 with 3. And then do we have a 3 or a, let's see what else we need. So we need a 3, and then I think we need a -1 or something. No. We need 3. We need 3 or a 1. Yeah, because, no, actually 1 wouldn't work. Well, let's just calculate it. So let's say I minus 1 equals 2. So this is 3. And then for this, what's this going to be? This is going to be -1. Yeah, so we need -1. That's what it was. We don't have -1. We don't have 3, so we can't do anything there. Okay, now we move on, and we incremented this prefix sum, so it's going to be -9. So 7, do we have it? No, we don't, so we're going to put it in our cache. 4, and do we have, so we need 9, or, so 9 will give us 2. What will give us -2 will give us, we need 5. So we need 9 or 5, we don't have it, so we're going to move on. And as always, do the prefix sum here. So this is -2. 8, do we have it? No, we don't. So we're going to store it at index 5. And do we have 10? No, we don't. And we need 6 as well. We don't have that either. And our sum is now 6. Okay. So for 1, we have a 1 at index 3. So we need to calculate that prefix sum from that location where it was up until right before this number. So this, is this positive? Yes, it is. So we're just going to store that. So we're going to keep the old number because that's going to be better. And once again, do we have, we need to have -1, which we don't have, or we need 3, which we don't have either. And do the prefix sum here. So I'll do that. So we still haven't found like any valid array. For this, we need a 5 or a 1, and we do have a 1, and 1 is at index 3. So this is going to be the array that we're looking for. And so let's actually write in this prefix sum first. So basically the sum of this array is going to be 10 minus -10. That seems kind of wrong. Yeah, it's definitely wrong, right? Because this is all positive. Let's just double check this. So -9, -2, 6, 7, 10. So that part is right. Yeah, definitely doing something wrong here. 10. Oh, right. It's 10 minus -10, right? It's not 10 minus 10, so it's 20. So this is, yeah, 15, 18, 20. Yeah. So it's this number minus this number here, which is 20. So now we do have a valid array of 20, and we don't really need to store the array, right? We just need to store the sum of the array. So our result now is going to be 20 of this valid array here. And do we also need to store the 3? So do we have a 3? No, we don't. So we're going to store a 3 at index 7. And then we will go on to the next one. So this is going to be 15. Do we have, so what do we need here? We need 7. We do have a 7. So let's calculate this, like this will be valid, right? So this is going to be 15 minus -9, right? Yeah. So this is going to be 15 minus -9, which would be 24. So that's better than our old result. And that's basically representing this right here. And let's just double check that. So 15 plus 9, yeah, 24. Okay. So that's going to be our best thing so far. And then we're going to store the 5. Do we have any 5s? No, we don't. So we're going to store that at index 8. And by the way, so did we have, so 7 would work, and also what would give us -2? So 3 would give us -2. That would work as well. We do have a 3. 3's right here. And what's this prefix sum going to be? So this prefix sum is going to be 15 minus 7, which is just 8. So that's smaller than the other one. So we're going to go with this one. Yeah, and then 5 is going to be at index 8. Yeah, and we didn't have it before. Okay. Then we go to our last number, so 7. Our prefix total is 22. Do we have a 7? Yes, we do. What's this like sum location? This is going to be 15 minus -9. So that'll be 24. Yeah. So we want to keep the old 7 because this prefix sum for the old 7 is positive. So the old 7 is going to be better. So we're not going to put in this 7. We're going to keep the old 7. Now, do we have values for the 7? Yes, we do. So we need a 9. We don't have a 9, but we do have a 5. Right? So 5 minus 7 would be -2. And then for the 5, the location's over here. So what's this prefix sum here? This is going to be 22 minus 10, which is 12, which is worse than our old result. So our best result was 24 for this one, I believe. Yeah. So hopefully that makes sense. The parts that you need to cover are A, prefix sum, B, when you have duplicate numbers, figure out what sum the old number contributes. If it's negative, get rid of it. If it's positive, keep the old one because it'll be better. And yeah, and then for each number, there will be 2 complements. There will be the one that gives you -k and k because absolute value. If you didn't notice that, you're basically just going to hit an edge case where you have that error. So yeah, let's take a look at the code. The code is pretty straightforward. So like I said, here's my prefix sum. I use an object. You can use an array. I like the object because I like the empty array. You could also have an edge case or like an if statement. So essentially, prefix -1 is going to be 0 because the prefix sum of an array from I to j, if you're trying to calculate this is going to be like prefixes of j minus prefixes of I minus 1. And if I is 0, this is going to be out of bounds, but you can have like an if statement or something to handle that. So I just use a dictionary instead. So we have a result. We just make it -infinity just to see if we can get it bigger. Then as we go through our numbers, we add it to the prefix sum. We calculate complement 1, which is v minus k. So in our cases, like let's say k equals 2, our value is 5. So we're going to do like 5 minus 3. Or 5 minus 2, that'll give us 3. So that's one value, right? Because 3 minus 5 will give us -2. And the other value is v plus k. So once again, if our value is 5 and our k is 2, this will give us 7 because 7 minus 5 is 2. So essentially, you're getting both the plus and minus k this way. So you get one complement you check, Is it in, like, have we seen it before? If we have seen it before, let's get its index and let's figure out from the prefix sum what that sum is going to be and maximize our result. Then we check the other complement, same thing. Is it in here? Could obviously clean this up a little bit because this is repeated code, but not that much. If it's in there, get its location, do the same thing, right? Just get the prefix sum for the array that it would make. Now finally you have your two cases for actually putting your number into the locations. If it's not in there already, just throw it in. But if it is in there already, I basically had this, but you can make this a little bit cleaner. So I had the old sum that it contributed, which is just the prefix sum of this current index minus the index right before where it was. And the new sum that it will contribute is just the current value. And then I just check like which one's better. If the new value is better, put in the new value. If the old value is better, keep the old value. Then finally at the end, you just return your result if it's not negative infinity, if we did find something. If it is negative infinity, we didn't find anything, so we just return 0. And so this is going to be O of n runtime. And the space is going to be O of n for the prefix sum. You could do some stuff like write over your nums array if you wanted O of 1. I guess that would, well, no, because you still have the location array. So I guess either way, you need the locations and the prefixes. So I don't think you can have, you probably can't like have both of them in here. But either way, writing over input's not good anyway. So I don't think you can make it less than O of n. And this is basically as good as it gets for this one. So we can submit. And all the solutions are kind of close here. So just depending on, you can see like these are all of them. If you just run it a bunch of times, sometimes you'll get 100%, sometimes you'll get like a little bit less, but it's roughly all the same. Space, I guess we can see how people did in space. I'm guessing, yeah, it's all pretty close as well because there's just like so many ways you can do it. So I do think it's a nice problem because you use prefix sums, you do that, you kind of have that like more complicated two sum, and then you need to figure out like, okay, well, I guess basically Cadane. So you're kind of using Cadane and prefix sums together. And it did kind of have like a low acceptance rate. And I will say the hard problem for this contest actually had a high acceptance rate. And it's a 7-point problem. And I think it's definitely shouldn't be a 7-point problem. I think this one's like around the same difficulty, if not harder. Yeah, so that's going to be all for this one. And then I will combine the hard problem and the medium one, because they're basically the same problem, into one video. And I'll release that in a little bit. It shouldn't be too bad. Like it's probably one of the easiest 7-point problems we've had so far. So definitely a pretty easy contest. And I'll definitely release that soon. And if you did like this video, please like it and please subscribe to the channel. And I'll see you in the next one. Thanks for watching.